So, welcome again. Now we are going to cover some very important part that is called applications of Schrodinger wave equation. So, let us have the conceptual build-up of the topics required to study this. So, we need to study the solution of 1D Schrodinger equation for a free particle, and it is also referred to the Gaussian wave packet. Okay. Then particle in a box, particle in a finite well, and linear harmonic oscillator. Then we will learn reflection and transmission by a step potential and by rectangular barrier. And then we will move towards particle in 3D box, density of states, and free electron theory of metal. And this angular momentum we are not going to cover right now. So let us strike it down. So let us have the conceptual build-up. So let us first understand the Schrodinger equation once again so that we could move ahead phrase. So recall a particle can be represented by a wave packet. We could represent a particle by wave packet, which is formed by superimposing the plane waves of different wave numbers. Okay, so particle is nothing but the superimposition of different waves. Okay, this is first wave, this is second wave, this is third wave. When this you superimpose, you get something like this. Okay, and this is what is actually the wave packet for any particle. Okay, and the velocity of particle is actually the velocity of the group, whole group. So we know that already. So now we are in search of wave equation. We are trying to find wave equation which describes the whole packet by wave function psi. And such wave function would be obviously the most fundamental theory for our quantum mechanics. So hence they are to be guessed, because if something is so much fundamental, then how could you derive such a fundamental thing by something other? Okay, so you guess that fundamental theory by applying the logical human thought in unconventional manner. And when you try to find the truthfulness of such fundamental wave function, it will depend on how accurate the theoretical results are with the experimental results. Such a wave function we have actually found and discussed a few topics back. We call that Schrodinger wave equation. Okay, and it has two different forms. The first form is time independent. The second form is time dependent. And here are two: time dependent and time independent Schrodinger equation. And this is yes, not the time independent Schrodinger equation. So let me tell you something in detail right now so that you easily remember. When you come to time dependent Schrodinger equation, this is nothing but energy is equal to kinetic energy plus potential energy. And they are not in the conventional classical form, they are just in the form of operator. So you could get your psi operated by each of them. We multiplied psi in the both hand sides of the equation. So this is what we have. And till now we know that okay, the energy operator is nothing but iota h bar d by dt, and kinetic energy operator is actually momentum's operator s squared divided by 2m, and this is nothing but potential energy only. So when you apply psi, okay, you actually get these terms because momentum s square divided by 2m will give you kinetic energy minus h bar s square by 2m, this delta square. Okay, so now let us try to understand statistical interpretation of wave function and the conservation of probability. One should know that the wave function associated with the particle has a statistical interpretation associated with it, and we call it the Max Born principle. Okay, this whole line is Max Born's principle. So it says that if a particle is associated with the wave function psi, which is a function of r and t, then the probability of finding the particle at the time t with the volume within the volume dV about point r is given by this value. Okay, where this is the complex conjugate, this is the normal wave function, this is the volume element, and when you integrate the whole thing, you get this value, that is probability. So probability is this value. Okay, so let me tell you, when you multiply the complex conjugate of wave function with the wave function, you actually get this value, and we call it probability density or position probability density. And as the probability of finding the particle somewhere in the whole space must be unity, so we can write this value. In mathematical language, this is done to satisfy the normalization constant as well, so that there should be the wave function must be normalized. So we can write that because somewhere particle has to exist in this space. So overall probability should be 100%, or in the integer or rational number form it should be 1. Now let us move towards conservation of probability. So we understand that the probability of finding the particle over whole space must be conserved. That means normalization integral should be independent of time. If it is to be conserved over all the space, that means the whole normalization integral should be independent of time. Okay. Hence, as per the mathematics, when you apply the mathematics, the time derivative of the normalization integral should be 0. So when you find the time integral of this value, it should be 0. Okay. And now we are going to find the proof of above condition, that when you take the time derivative of the integrand, and in this integrand is nothing but it is done over all the space and it is probability. So partial derivative of probability is 0 over all the space, over all the space. Okay, this is what we are trying to prove. So let us use this Schrodinger's wave equation, and we could write the following two equations. The first equation will be written for the psi, that is wave function. The second equation will be written for the conjugate, complex conjugate of psi. So the first equation is this. That is, we have just used the time dependent form of Schrodinger equation. Time dependent form is actually related to this value. We just discussed that, and it is for this value psi only, and next is for the complex conjugate of that psi. Okay, and now we could multiply equation 4 by the cross relative of psi, that is complex conjugate of psi, and the equation 5 by the cross relative of uh, complex conjugate of psi, that is psi itself. Okay, I am calling cross relative that for psi you need to use psi asterisk, that is complex conjugate, and for complex conjugate you should use this value. Okay, so we multiplied with this whole equation with complex conjugate of psi for with the whole equation, and in the second equation we just used psi, and then when we subtract we actually get this value. Okay, and it is pretty simple to do that, not a much mathematical skill is required. Just multiply that, subtract that, you will get this value. Okay, so let us note it down and now move to our parent equation, that is this. So when we try to find the time derivative of this probability, which is all over the space, let us not forget that integration is all space. Even if we are not writing it, we have already made it clear. So when this differentiation enters into that, so it is in the form of, let me explain, it is form of the fx multiplied with gx. So the ultimate formula is fx comes out as constant and gx is differentiated, then gx comes out and fx is differentiated. We call it chain rule. Okay, so we have used this to get this, but as soon as you find this, you know that we already have this value here. Okay, these two are same. So we will substitute the value of this equation into the equation 7. So now we have value of RHS of equation 7 in equation 6. So we will substitute the value from 6 into 7 to get this. And it is iota h bar upon 2m. Integration opens the big bracket, and inside the bracket you will get this value. Okay, that one side it is psi asterisk double derivative of psi minus psi double derivative of psi asterisk, and you can take out the del operator as common, and within that you could write this, that is psi asterisk del psi minus psi del psi asterisk. Okay, and let me tell you, this is here by mistake. It should not be here because we have taken it out as a common factor. And now let us call the RHS of above equation J as this. Okay, so we are writing this whole thing as J. So what we will get, let me show you. When you substitute equation 9 into equation 8, we actually get this, that time derivative of the probability, okay, over all the space is this value, that is del dot J dV over the volume. And when you apply the Gauss divergence theorem, okay, this whole RHS will get termed into this. Okay, that is volume integral will convert into the surface integral, and this happens because you have applied the Gauss divergence theorem. So this is what we have got, equation 10. Not to forget, this is the value which we have written inside is psi asterisk psi, and psi asterisk is nothing but the complex conjugate of psi. Okay, and they both are function of r and t. Now let us move towards final conclusion, that how do we prove equation 3 from equation 10. And equation 3 is nothing but it is time derivative of the probability all over the space is going to be 0. This is what we are trying to prove, and we have equation 10. So let us do that. So for normalization, volume V extends to all the space because that is the way we have defined it. Okay, this is all over the space. Let me tell you, we have written it somewhere else. This, okay, this is all the space. So when you take volume to the whole space, so surface of that volume will be also infinite. Okay, for infinite volume, the surface associated with that volume is going to be infinite. And since the square integrable wave function, you should remember it, that is square integrable wave function, that is function of this form, vanishes at the last distance. Okay, that they vanishes and the surface integral becomes 0. You need to remember this argument because right now we are not going to go into such a deeper mathematical calculus. Okay, hence we finally got the equation 10 in this form. Because your surface integral is going to become 0, so this is going to become 0. So we are here required to write the argument only by using the mathematical results and not the mathematical procedure or a step. Now equation 10 can also be manipulated to be converted into probability current density. So this is equation 10. Okay, this is equation 10, that is you are taking the time derivative of probability over all the space associated with that particle whose wave function is psi, that is equal to minus integration over the surface of this j dot ds, and where ds is the elemental area, ds is elemental surface area. Okay, so let us try to interpret it properly. So this left hand side is rate of change of probability of finding the particle in volume V. Okay, this is actually rate of change, and in the right hand side we are going to get probability flux passing through the surface S. This is how it is mathematically defined. Hence J is nothing but probability current density. So mathematical form we could write J as this, that rate of change of probability with respect to time is going to be negative of divergence of J. Okay, or you could bring it to the left side to write it in this form, and this is nothing but equation of continuity. Why do we call it equation of continuity? Because we have a very similar equation in fluid mechanics as well. Okay, it is a familiar equation from fluid mechanics. It talks about conservation of matter in a fluid of density P and current density J in the arbitrary medium where there is no source or sink. Things are just passing, nothing is being created or destroyed. That means there is no source or sink, and we call this equation as equation of continuity. Now let us interpret the equation of continuity. Interpretation of equation of continuity. So if suppose that RHS is going to be 0, means this is going to be constant. The way it is defined. If you are differentiating something and the result is 0, means whatever you are differentiating, that is constant from this equation. Okay, if this is 0, then this will give you this value. P is to be constant. Okay. So in this way, we could call it a stationary state. And the probability current density could also be written as in this format. That is the real part of this value written under the square bracket. That it is psi asterisk h bar divided by iota m del psi. And RE stands, this is the class 12 level thing, RE stands for real part of whatever it is written. And note that this is actually h bar by Im. Del is actually the momentum divided by mass, and momentum is nothing but minus iota h bar del. Okay, and when you this minus could be there also, so we could write the same thing as h bar iota delta. So this is what they have written, and here it is m as well. Mass is divided both side. So momentum divided by mass. Momentum divided by mass is nothing but velocity. Okay. So this is velocity. Hence equation 12 can be written as P multiplied by V. Okay. Where this P is nothing but this probability density, or um, hence probability density, and hence in the words probability density times velocity is nothing but probability current density. That is what we have done till now. And now we will start the another big theorem in quantum mechanics, that is Ehrenfest theorem. Okay, so we need to know that what is correspondence principle at first to understand the Ehrenfest theorem. So correspondence principle says that, as the name says, it corresponds to something, correspond or connect to something, and it connect quantum to classical mechanics. How? Let us see. It says quantum mechanics reduces to classical mechanics in a limit where the principal quantum number n goes towards infinity. When the things or samples or principal quantum number, whatever there is, it is very big, then it actually turns into classical mechanics. In other words, average motion of wave packet should agree to the motion of the classical particle. That is why we write that velocity of particle v is actually velocity of the group of the wave. Okay, and this whole correspondence principle was actually proven true by P. Ehrenfest in 1927. See how. This is the statement of Ehrenfest theorem. It says, according to Ehrenfest theorem, the equation of the motion of expectation value, that is expectation value of momentum and expectation value of position for a wave packet, is identical to the second law of the Newton. Second law of Newton says that rate of change of momentum is force. Rate of change of momentum is force. So in the similar fashion, we could connect the expectation values of momentum and position to the second law of Newton. Okay, so it is nothing but momentum is mass times velocity. Okay, so here we have taken mass m and velocity is rate of change of position expectation value. So in that way, rate of change of expectation value of position is momentum divided by mass. That is what classically we need to have. Okay, and as mm, rate of change of momentum is actually some kind of force quantity, and force quantity is negative gradient of something. So we could also write it to be negative of the expectation of the gradient of v. So you should know that force is the way it is defined. Okay, force is the negative gradient of some scalar function v. Conservative force, not all forces. Because let me tell you, mathematically, for conservative force F, when you take the curl of that force, it comes out to be 0. And whenever the curl of any quantity is 0, that quantity itself is the negative gradient of some scalar function. So this is where it is defined. So rate of change of momentum's expectation value is nothing but negative expectation value of gradient of v. Now we have two equations. The equation 1 is here, that is, it is saying rate of change of position is momentum by mass, and they both are expectation values of position and momentum. In the second, rate of change of momentum is actually negative gradient of the some kind of scalar function, which we also call potential. Now let us prove equation 1. Equation 1 says rate of change of position with respect to time is expectation value of momentum divided by m. So let us try to prove it. So at first let us state what is expectation value of x. So we know that expectation value of any quantity x is written in the caret left and right, and it is in this format. Okay, so whatever you are trying, suppose that if you are trying to find the expectation value of operator g, so you will write it inside the caret, then you will write integration, then you will write psi asterisk this operator, then psi, then dx. This is the way it is mathematically defined. We have studied it already. So just you simplify it mathematically, okay, by finding the rate of change of expectation value of x. So when we are doing that, we are trying to find dy by dt of x. It is going to be dy by dt integration of this expectation value. Okay, and when you break in this d by t inside of the integrand, it is going to be in this format. Let me tell you again, it is the same thing that you are differentiating fx multiplied by gx. So we are following the same chain rule. Sorry, not chain rule, but the product rule. Now we are required to need values, because when we did that, we got d psi by dt and d psi asterisk by dt. So we need to find these values from the Schrodinger's wave equation. So hence we could apply the Schrodinger's wave equation to both the wave function, that is the psi itself, and its complex conjugate psi asterisk. Using the above two relation, the equation 3 could be turned into this. And how we did nothing but we just got the values, like you just take out d psi by dt and d psi asterisk by dt and put it here and here. So what you will get? You will get this expression. Okay, it is integration of psi asterisk 1 upon iota h bar, bracket opens, and inside the bracket we are going to get minus h bar square by 2m del square psi plus v psi, and v is nothing but the potential, plus again 1 upon iota h bar under bracket, the same way we have described uh, for psi asterisk. Okay, and x psi dr. So we could then write the whole thing in this format, okay, that it is iota h bar upon 2m integration under the big square bracket psi asterisk s del square psi minus psi square del asterisk x psi bracket close dr. Now in this you can apply the Green's first identity to get this value, and this is where the memorization plus understanding M is coming into play. Green's first identity, you must remember, is of this format, okay. And this equation, the first term of the RHS, is going to be 0 as the volume under the consideration is entire space, and hence surface would also be infinite. Hence we have already learned that a square integration of surface integral is 0. So this whole thing is going to cancel out, and we have left only with this. And it happened when we use the Green's first identity over this term only. So learn it very correctly. Thus we are left with this only, okay. And again we will have to use the Green's identity, okay. And when you again use the Green's identity, the surface integral again vanishes, and we are finally left with this equation 5. And these are nothing much to worry about. This is what you need to practice enough, that in 2 steps we are trying to apply the Green's theorem, okay. And when you substitute equation 5 into 4, you get this value. And as we know that del square x psi is nothing but x del square psi plus 2 d psi by dx, okay. This you should know mathematically earlier. Just go and find it. You will get this value only. Hence, this derivative of the expectation value of x is going to be this. And finally, when you do the mathematical manipulation, you will find that it is nothing but momentum by mass. So we have got it for x. Similarly, we could do it for y and z direction, and finally you can get what we are required to prove, that is the rate of change of position is velocity, that means momentum divided by mass, and they all are in expectation value format. So we are done with the first equation. Now we are left with this second equation. Now from calculating the time derivative of this momentum in x direction, we get this expression, and when expand it, it got to this. An expansion means you are just using this d by t into this. You are breaking it into, considering this as fx and considering this as gx. So you did that. Now again we need to have the values of d psi by dr, dr and d psi asterisk by dr. Okay, here r could be replaced by x, y, and z. Okay, and thus equation 6 could be rewritten in this format. Now we are required to use the Green's second identity, which is this. Okay, Green's second identity is written here. And when you use the Green's second identity, okay, the first integral of the RHS is 0. What is the first integral on this RSH? It is going to be 0. Okay, and second integral gives us simply this value, which is nothing but the expectation value of partial derivative of v with respect to dx, with respect to x. Okay, so finally equation 7 turns out to be this, and you can do the same for y and z direction too, and finally you can prove that dy dt, rate of change of expectation value of momentum, is negative of the expectation value of the gradient of the scalar potential V. That is what we call the Ehrenfest theorem, and it actually what Ehrenfest theorem does, it proves the correspondence principle true. It proves correspondence principle true, and this is you need practice 5 to 6 times. Practice is required to memorize it. Okay. And this is the fundamental theorem in quantum mechanics, so we must do it. Now we are left with eigenvalue, eigenfunction, and degeneracy. So when any operator O, when operated on the sum wave function psi, which gives the result some constant times the same wave function. Like suppose that we have a operator O, which is we are applying on psi, and then we are getting some constant C multiplied with psi. If that is the case, then we are on the spatial platform, and we call this function as eigenfunction, and we call this constant as eigenvalue. Okay. So mathematically the same case, what we just did, that you apply the operator G. Look, we identify operator by this cap. So this is the operator. When we apply the operator G on psi, we get some constant, and the answer is some constant multiplied by the wave function or the psi itself. Okay. So in that case, the psi is eigenfunction and this constant A is eigenvalue. Okay. For example, consider this wave function exponential 2x. So when you take the operator as momentum operator, that is this is the momentum operator. We know that it is minus iota h bar del. So when you do the same thing, you get minus iota h bar, and for del you need to use partial derivative of exponential 2x. When you do that, you get minus iota h bar 2 exponential 2x or minus 2 iota h bar and then psi, because exponential 2x is nothing but psi. So this is the constant A and this is psi again. So if this is the case, then we are on a special platform. This psi is nothing but eigenfunction. This A is nothing but eigenvalue for that operator. Okay. And what is degeneracy? It is very simple concept. When for many linearly independent eigenfunction have the same eigenvalue, we have like many linearly independent eigenfunction and they all have same eigenvalue, then eigenvalue is said to be degenerate. Okay. And what is parity? So parity of two cases, one for non-degenerate, one for degenerate eigenvalues. So for non-degenerate cases, okay, the expression for psi, which is function of x, and then psi, which is function of minus x, can differ only for a multiplicative constant. So for even parity, we have this condition. For odd parity, we have this condition. Okay, the difference is that when you the function of minus x and when the function of x is going to be same, we call it even parity. And when the function of minus x and when the function of x is not same, but they differ with the negative sign, they are odd parity. And for degenerate eigenvalues, okay, psi of minus x is not required to be a multiple of psi of x. Thus, they both are linearly independent solutions of same eigenvalue. Okay. Therefore, any linear combination of such wave function is also an eigenfunction. So, suppose that if you add them, then we can call it this psi plus x, and suppose if you subtract them, you call it psi minus x. Okay. And then you can call that psi plus x have even parity and psi minus x have odd parity. So that is what we need to learn till now. And just you understand the degeneracy, this statement very, very clearly. Okay. For linearly independent eigenfunction if they are corresponding to same eigenvalue. The eigenvalue is said to be degenerate. Okay, for psi1, psi2, psi3, when they have same eigenvalue a only, okay, they can have a1, a2, or a3, but that is not the case. They are a only, they have same eigenvalue, then they all are said to be degenerate eigenvalue. Okay, and psi1, psi2, psi3 are linearly independent. That means when you multiply some special constant alpha1 to psi1, some special constant alpha2 to psi2, and some special constant alpha3 to a special constant means just constant, no need to write special. And when you add them all, they turns out to be 0. In that case, they are linearly independent. Okay, so this is what we are required to learn till now. So let us meet in the next lecture.